nego Elopšovi svakog. Više komedija nego film.
Da, ajde. Nemoj da otkrivaš. Možemo da počnemo, ajde, da stignemo na vreme.
Hello everyone, my name is Vlada and these are my friends Luka and Ivan and
Tiše rečemo, my name is Vlada.
our presentation is the dangers of electricity. Now I know everyone wants to see these live experiments, but before we delve into the live part of this presentation, we want to give you a quick heads up on electrical safety. So let's start. The human body and electricity. The invention of electricity has revolutionized the world, forever changing the way we work, communicate, and live our daily lives. While incredibly useful, electrical energy can be quite dangerous if not handled properly. Electricity can pose a big threat to human life or even environment if mishandled or underestimated.
So essentially, when we get shocked, we will first experience the electrical shock itself. Though the electrical shock itself really hurts, we won't feel it as soon as we disconnect from the circuit. Actually, the electrical shock itself is the least common way to die due to electricity. There are multiple effects that electricity has on the body, actually, and they can be categorized into multiple categories. We've only mentioned a few, really broad representation of the things electricity can make you. So we can categorize the effects as mechanical, thermal, chemical, and the last symptom of the shock is death. Thermal effects are essentially muscle spasms and involuntarily nerve congestion, or actually nerve impulses. Thermal effects are actually burns. So when you're exposed to a high current for a long amount of time, you will get burned from the electricity because current makes heat with it. And the chemical effects is essentially electrolysis of the bodily fluids like blood and tissues.
Okay. Hazards of direct current versus alternating current. Both AC and DC electricity can be dangerous. AC poses a greater threat to a human body. This is because AC reverses direction constantly, about 50 or 60 times per second. And of course, both can be extremely dangerous in certain conditions though, so we have to be careful like Luka.
Another reason as to why AC is actually more dangerous than DC is parasitic capacitance. As you know, capacitance doesn't really exist on DC, as DC blocks capacitance. But essentially how this works is everything can be a capacitor, even your body. So if I, for example, go ahead and touch the live wire there, even though I'm not directly connected to the ground, I'm not grounded because my shoes are actually insulators, I'm probably going to get shocked because of the capacitance that is built between the ground and me. Okay. Now to the part that you all...
First of all, I should do disclaimer to my teachers. Please sit back, relax, enjoy the show. I have tested this a fair few times at home yesterday. Safety tested all the equipment.
Your family members are safe.
My family members are... No, I am speaking God honest truth. Now, so please, I know I may not look like it, but I actually know what I'm doing. So, that's the beginning. Now that we actually have your attention, because safety presentations are boring to be honest, let's start with this. So what makes me qualified? So what actually makes me qualified? We have a comprehensive list of 8 things, such as nothing, nothing, and nothing, because I really had no qualifications. But I'm what you call, forgive me, pardon my French, but a professional idiot. So here we have a switching power supply, a 36 watt power supply to be more precise. Now, what does 36 watts mean? Well, next up, please. So, oh yeah, actually, sorry. So this is a quick little chart. You may remember from Mr. Zoran Osic's classes at the beginning of our first year, which I bet you don't, because I don't either. Which you can see how much current is needed to kill a person, and do whatever it is, but we're only interested in the death part. So for DC, direct current, over 300 milliamps of current can kill you. Next slide. So we know this formula for power. Power equals voltage times current, and from which we derive the formula current equals power divided by voltage. This is a 36 watt power supply. What does it mean? Next slide. So at 36 watts, if we set it to 12 volts, that should result of a short circuit current of 3 amps. Only a few hundred times more than the dead lethal 300 milliamps. Now let's actually measure 12 volts. Now you may not be able to see the instrument, but yeah, if we set it to 12 something volts, whatever, it shouldn't really make a difference. So, as I hold the ground wire, which is ground, nothing really happens. No current flows through my body because it's ground. But as soon as I touch this hot wire, 3 amps should flow through my right hand, through my heart, making it explode, through my left hand, and I should be dead before I even hit the floor. So, got 3, 2, 1, nothing. And this is really 12 volts, you can check it. Now, okay, so it isn't volts, it isn't amps that kill. If you were ever near a high dangerous electricity source, I don't know about you, but I was, it always says high voltage, not high current. So it's surely gotta be voltage that kills. Next slide, please. So this is a little DC to DC power amplifier circuit. I won't go into too much detail, but basically we have a low voltage DC source that gets through these. It isn't really a good scheme, but there should be an integrated circuit that turns it to AC, goes through a transistor, steps it up a little bit, and charges a capacitor, goes through another transistor, and a few diodes that rectify the voltage and turn it into DC, giving us a few high voltage DC sparks. Now, our professor should probably know that electricity needs around 1 kilovolt to jump a gap of 1 voltage. Here we have this little circuit integrated into this lovely device, which if I turn on, you can see the gap is around 1 centimeter. So what would that be? 10,000 volts. Now, you know people die from 220 volts, so something like this should be enough to kill me. Now, since your brain doesn't really let you hurt yourself, I would ask one of my assistants to come and shock me, and hopefully kill me. Okay, Ivan, push please. Okay, I mean, no, send it a little bit.
Masochista.
Well, I'm not that. Well, you know, we have that high current, high voltage. What else do we have left? Well, this is actually something new we have started learning about at the beginning of our second year in basics of electrical engineering. It's called frequency.
So,
So we have high voltage, high current, but we haven't had high frequency. So this here in front of me is a small Tesla coil. You heard about it, I won't go into too much detail. But basically what it does, don't let size fool you, you're gonna see. It turns low voltage DC with this little transistor, switches it back into AC, steps it up a few hundred times, and gives me an output voltage of a few hundred volts and a few thousand hertz. So as I turn it on, if few amps, few thousand volts didn't kill me, a few hundred volts and many thousands of hertz should finally do the job. Hopefully. Now, it's really small, unfortunately, but if you see this little purple thing, now those are actually electrons ionizing, charging the air particles and ionizing. And it really does pack a punch. We have this ironic piece of paper that says electrical state. I don't know who wrote that there. But if we bring it, you can see that it burns. Thanks. So if I touch this output, finally, high current, high voltage, high frequency should kill me, right? So tell my mama lover. 3, 2, 1. Well, it just burns. Well, the truth is, I've done nothing but deceive you for the past 5 minutes. Well, not really deceive you, I just wrapped all this truth, that one little lie in a whole bunch of truth. let's go back to our black box. So really 36 watts does mean 3 amps at 12 volts. However, that's short circuit current. I am a big resistor, not open circuit or short circuit. So if we divide the 12 volts with my body resistance, which I have measured previously, now I'm sweating so it might be a bit less, that's like 0.0005 milliamps. That basically rounds down to 0. So when I touched those, no current was passing through me. Excellent. So this thing, well, why I didn't die of these 10,000 volts? Because the thing switches DC, not AC. And every pulse you hear lasts only a few microseconds. So when we plug it into a formula, you can see that 0.0064 joules, and enough energy to kill a person is around 100 joules. So I wasn't anywhere near dying. Next slide. So now, also I didn't die when I touched the little Tesla. Now let me turn it off. Now, there are many reasons. First of all, the high frequency is actually less dangerous to us than low frequency. Now, you might wonder why is that? Well, many reasons, which I won't get into that deep, but first of all is that our nerves, being made of blood and flesh, really have some time to react. They operate at voltages of around a few microvolts, so not a lot of current is needed to override them. But if that current oscillates 10,000 times a second, 1,000 times a second, when it gets to the sinusoidal peak, and then back to 0, your nerves simply don't have time to react and contract. So it just really burns. And the other reason is the skin effect. Well, it's really complicated. We won't be learning it in high school, I think, but if you go to the Faculty of Electrical Engineering, you will learn something like this. High-frequency particles tend to float on top of a conductor rather than penetrate down to its center. So if I was exposed to really high-frequency particles, they would most likely go above my skin, down to the ground, dissipating, and I wouldn't die. Next slide. Now, actually, if I survived 3 amps, thousands of volts, hundreds of thousands of hertz, if I put my finger into a wall outlet, what should I do? 220 volts, 4 amps, 50 hertz, right? Well, not really. Well, Ohm's law really does state that that should be the current, but you can throw it out the window in this example, because there's also something called dielectric breakdown. Even though my skin is 250 kilo ohms to a small DC voltage, through a high AC voltage, it would just penetrate my skin, go to my low resistant muscles and whatever not, go straight through me and kill me. So that's why you should never stick your finger into a wall outlet. Here we have an example of another high frequency. Thank you for your attention.
Čula se Karića da priča, razumeš?
Pa mislim, možda je, ali više sam ovo ja se pržim pred vama. Sve ću.
Ovo je Marija.